Welcome to the next video in the group theory series. In this video, we will define g to an exponent n for every integer n. You can see a preview of what will be in this video here. Okay. The obvious case is when n is strictly, that should be strictly greater than 0. When n is strictly greater than 0, then g to the n means taking the product of g with itself n times. So it's just a shorthand for something that we could otherwise write in principle, although we would never want to. So the notation is an invention for the sake of laziness, in a sense. Anyway, if n is equal to 0, right, the project is to define this for all integers. We've only dealt with the positive integers for now. So if n is equal to 0, then what is it? Well, somewhat naturally, we define it, right? G to the 0 is equal to 1. And if n is negative, then g to the n is the product of g inverse with itself negative n times. Notice that in this last case, negative n is a strictly positive number, so it makes sense to use negative n to count the number of instances of G inverse. Of course, we will also correspondingly define for additive groups the notation of n times G. Right, and that is, threatens to look like group product notation. So we have to be very clear that when we're talking about an additive group, this is an integer n, not necessarily a group element. In fact, shouldn't be a group element if they're being multiplied in an additive group, and this g being a group element. Anyway, when n is positive, we add g to itself n times. When n is 0, it comes out to the identity. And when n is negative, it is subtracted from itself negative n times. Okay. Returning now to the multiplicative notation, you should notice that if n is negative, then this equation follows immediately from definitions. Because after all, right, g to a negative exponent means g inverse product with itself negative n times. Well, a negative n exponent over here is a positive exponent, meaning we take, right, we product this with itself negative n times. So they end up basically just meaning the same thing. Okay, this equation is also true if n is 0, and that's quite trivial. If n is strictly greater than 1, that actually turns out to be the case that requires a little bit of extra care, although not too much. I leave it to the viewer to prove. You will need to help yourself to the fact that G inverse inverse is the same thing as G. And this is proved in a later video titled Basic Group Theorems. Otherwise, the viewer is encouraged to try to prove that this equation holds also in the case when n is strictly positive. Okay, much of the rest of this video is about proving that the familiar exponent laws hold. We will prove this by cases, starting with g to the m plus n is equal to g to the m g to the n. And this is a result that is easy to believe and want, and the proof proceeds by cases. The easiest, or at least among the easiest cases, is when both m and n are strictly positive. In this case, g to the m plus n just means this many, because it is positive, this many copies of g product with itself. So that's what we see here. Now we can simply count it differently, right? We can count up the first m, followed by counting up the next n, and then that first group of m we wrap into a single expression of g to the m, and likewise for g to the n, and that's that. Um, okay, moving on to the case when either m or n is equal to 0. This is even easier, right? It's easier because one of these being 0 means g to the m plus n it simplifies immediately down to either g to the m or g to the n, and then that is also what you get on the other side by a very simple argument. So anyway, I leave most of that to the viewer to fill in. Now let's consider the case where both m and n are strictly negative. Notice in this case that we get these positive numbers, negative m and negative n. That's important because we use the strictly positive numbers to do the counting. So we can start this time from g to the m, g to the n on the left-hand side, expand that out by definition. Because these are strictly negative numbers, it's a product of g inverse with itself, negative m and negative n times respectively. Now, if we simply count this entire collection as negative n m minus n instances of g inverse, then notice that this being the same thing as negative m plus n, that being a positive number, m plus n being a negative number, then if you check the definition of g to the m plus n for a negative number m plus n, it is the same thing as this, right? G inverse product with itself, negative m plus n times. Okay, that was a relatively harder one just because of how much extra, how many extra words it took, if, even if the logic wasn't that bad. But now let's consider the possibly even subtler case of when one of these two numbers is negative and the other one is positive. Now, without loss of generality, I will assume that m is the negative one, n is the positive one. Still, we have to break it down into even further cases. So the first subcase here that I'll consider is when negative m, remember, right, because m is negative, then negative m is positive. And it may be that negative m could be bigger or smaller than n. So let's consider for our first assumption that negative m is less than or equal to n. Now, what this basically means is that when we're thinking about g to the m, and we know that that corresponds to negative m products of g inverse, that's what we're going to get over here. We're going to have n products of g. We know that these are going to do some canceling, and when negative m is less than or equal to n, this means that either they entirely cancel when they're equal, or there's going to be some extra g's left over after the cancellation. That's the intuition anyway. Now, applying that here, we know that every single one of these negative m instances of G inverse are going to cancel with precisely that many instances of G here. And that means that n minus negative m is going to count up what's left over, which is namely the instances of G that didn't cancel. That's what's left here. And n minus negative m is the same thing as m plus n, so we finally reach the right-hand side. Okay, in the remaining case where n is strictly less than m, almost the same thing happens. Only this time, all of the instances of G cancel, leaving only some instances of G inverse. So there are more negative exponent terms, right? More G inverses. and the positive exponent terms cancel out. That's the g's cancel out. So for all of these g, they each cancel with some g inverses. The g inverses that are left over are the negative m instances of g inverse from the original minus all the ones that canceled, which is minus n. And then that, by very similar logic to before, turns into negative m minus n, which is the same thing as m plus n. So that concludes my proof. If you're a little unfamiliar with the use of a without loss of generality proof, I have a little something for you here if you'd like to pause the video and take a look, but I'm gonna just keep going with the rest of the exponent laws. And so the next exponent law is going to be this power of a power law. G to the m to the n is the same thing as g to the mn. So the proof is similar to the previous one, and I've written it in the page to the left. So I won't talk it all out, right? You can see a bunch of stuff over here that doesn't give a complete proof, but it should give you the idea. I would like to just spend the rest of the video pointing out, or at least some of the rest of the video pointing out, that not every exponent law that you may be familiar with and hope exists for groups, not all of them hold for every group. So be careful with the exponent laws. You could hurt yourself. Not all of them carry over to groups. In particular, there are cases where g to the m, h to the m is not the same thing as gh to the m. To give a specific example, this fails when g is equal to the rotation, h is the reflection, and m is equal to 2 in d sub 2n, right, the dihedral group on n vertices. You can see over here a little discussion of that. But basically the problem is that not in every group can you swap GH for HG. A group is called commutative if GH equals HG. In a commutative group, this law does hold. For instance, in the case that m and n are both strictly positive, then we could take g to the m, h to the m, write it out as so many products. Then, due to commutativity, right, we can swap the g and the h around here, and we can swap and swap until eventually the h gets written right next to g. And then we can do it again, pulling another H over here and pulling another H until eventually every H gets paired up with G. And we know that they pair perfectly because there are M of them in each. And then we write these parentheses for emphasis, not because they're necessary, but we know that there are M instances of this product GH, and therefore, by definition, it's equal to that. The remaining cases, right? Recall that this was all under the assumption that M and N were both strictly positive. There are all of these remaining cases. Their proofs are similar to the proofs discussed earlier in this video, so I leave them also to the viewer. And here you see a brief note reiterating some of what I've already said about additive notation.